Significant figures. This one's a long one. Buckle up. This goes on for a while. I might go a little bit faster through some of the sections, but significant figures is especially important, maybe not as much for the intro physics courses, but more for the labs. When you write up the labs, you should be able to come up with the proper significant figures. Some instructors will really demand that you have the proper number of significant figures. Obviously, if you have too few, you're not going to get a very good answer. Tend to be a little bit looser sometimes with significant figures when making calculations. But there are two types of numbers that we often deal with in physics. We have exact numbers, which, as their name implies, are exact. And we have measured numbers, which have some uncertainty to them. Okay? So significant figures basically tell us how reliable is this figure out. In fact, the significant figure is a reliably known digit. The last significant figure is the most uncertain of all the digits. Okay? And again, we'll go through quite a bit of this. All non-zero digits are significant. So if there is a 1 through 9 in the decimal place, you know that that's a significant amount. It's the zeros which are tough. Zeros between non-zeros, they're significant. After a decimal place and another significant figure, they are considered to be significant. The easiest thing to do is write things in scientific notation, then there's no ambiguity in what is significant and what's not. But again, operations with significant figures, we're really talking about this concept of accuracy and precision. The least accurate number has the lowest number of significant figures. Actually, it should really be the least precise has the least number of significant figures. When multiplying or dividing two or more quantities, it's the number of significant figures which carries over to the answer. When you're doing addition and subtraction, it is the least accurate number of whatever you're adding or subtracting, which determines the outcome. Okay? Let's take a look at some examples, because that's really the easiest way to do this. And again, exact numbers, these are numbers which are, have infinite accuracy. We don't have to worry about them. Measure, you can never completely know what, a number is to an infinite amount of accuracy. Okay? So, exact numbers, 2 soccer balls. I mean, you wouldn't have like 2.3 soccer balls. 2 soccer balls, 4 pizzas. Those are exact numbers. Okay? We know there's either 2 soccer balls there or there aren't. We know there are either 4 pizzas there or there aren't. Okay? Yes, you can cut up pizzas, you can cut up soccer balls, but when we're talking about exact numbers, they are basically, in these cases, positive integers. Exact relationships are predefined values. 1 foot always equals 12 inches. 1 meter always equals 100 centimeters. There is no uncertainty in making those conversions, which will be introduced when the conversions are made. Compare that to measured values. Let's say that you're in chemistry class and you're measuring an amount of liquid. Okay, here's a graduated cylinder. You probably know what a graduated cylinder is. And we look and we see, okay, here's 15, 16, 17. It's between 17 and 18 milliliters. I look at it even closer, I'm like, well, it's a little closer to 18 than 17. How well do I know this figure? Well, I certainly know it better than to single milliliters. All right? It's definitely more than 17, it's definitely less than 18. But I need to sort of estimate where the tenth is. So in estimating, I thought I'd have an answer here. Well, okay, let's just do this. We look like we're more than halfway, so I would probably call that 17.6. Yeah, that would probably be a pretty good 17.6, maybe 17.7. What's the length? Again, here we have centimeters. We know we're between 1 and 2 centimeters right here. We can estimate better than the nearest millimeter, okay? 1, 2, 3, 4, 5, 6. So 1.6, again, we're a little more than halfway. How would we actually do that estimation? Again, our least reliable figure right here is this figure right here. Again, clearly it's greater than 1 but less than 2. Clearly it's 6 millimeters beyond 1, but not so clear as what that figure is right there. So when we do measurements and then we do mathematical operations on that, we have to preserve in terms of the uncertainty. In this case, we are uncertain to 1/10 of a millimeter. We have to preserve that through any other calculations that we do. All right. Can't guess any better than that. Same thing here. Okay? We know this better than to the nearest, again we're doing centimeters right here, better to the nearest millimeter, so we'd say, well, that is too imprecise given how good we can get this measurement. But I don't think we can get much better than 1/10 of a millimeter. So, you know, I can go this far, but to estimate any better than that, I'm not going to do any better than that. So really, when making measurements, we want to get the greatest number of significant figures we can, okay, within reason. So this would be the reasonable answer. Again, you can take a look at this one, do that estimate. 8 centimeters, okay, or 3 and 2.28 of an inch. Okay, so all but one of the significant figures are known with certainty. So the last significant figure is only the best possible estimate we have for that last digit that we're throwing in there. To indicate the precision of a measurement, the value recorded should also use all the digits with known certainty. Okay. In this case, we have a mass between 54.06 and 54.08. So we know it plus or minus 0.1 grams. So again, that digit right there is uncertain. It could be almost as low as 0.06, it could be almost as high as 0.08. Okay? Again, here's another measurement right here. This measurement right here has a much higher level of precision. This is only good to the nearest 100th. This one is actually good to 3 more significant figures. Okay? So to the nearest 100,000th of a gram. Okay. 4 rules. When reading a measured value, all non-zero digits should be counted as significant. Okay, anything from 1 to 9, those will be significant. There's a set of rules for determining if the zero in a measurement is significant or not. Does it add to the precision? Rule 1, zeros in the middle of numbers are likely. Any other digits, they're always significant. Zeros in the middle of a number other than 0 are always significant. So this 0 right here, in the 1/10, because we have even smaller values right there, we're going from the tenths to the hundredths to the thousandths, that's going to be significant. Zeros at the beginning of a number are not significant. They only act as placeholders. So here, these 2 zeros in front of 0.0834, okay, there's only 3 significant figures because that 0 just pushes it to a lower power of 10. Same thing here. 0.02907, only 4 significant figures there. Those zeros are placeholders that show you that the figure is actually smaller. Zeros at the end of a number and after a decimal point are significant. Okay, so here we have 138.200. There's no reason to have those zeros there unless those zeros have some significance. Therefore, they are significant. Zeros at the end of a number and before an implied decimal point may or may not be significant, so we don't always know. For instance, 100 is the 1 is definitely significant, but is only the 1 significant? Is the 10 significant? That 0? Is the 1 significant? We don't know. So let's do a few different, how many significant figures? Everything's non-zero, everything's significant. All digits count there. 6 digits there. In this case, we got placeholders. This 0, this 0, this 0 just pushes everything to a smaller power of 10. They have no significance there. So here, well, you only have 3 significant figures. Here, it's sort of a mixed bag. These 3 zeros are placeholders. All right? But the 2 zeros on the end, they're definitely significant because they wouldn't be there otherwise. If only the 239 were significant, you would keep the 2 zeros off. So 5 significant figures for that one. Here we have a decimal point right there, so that tells you that everything on the left-hand side is significant. So 5 significant figures. But this one is really uncertain. Are these 2 significant? Is this one significant? Normally, we assume, because it's not indicated, that there would only be 2 significant figures there. Scientific notation, everything there, it's significant. So for digits in front of the power of 10, everything counts. Here, everything's significant. The zeros have a non-zero on the left-hand side. The 0 is after a non-zero. Everything's significant. Okay? Again, scientific notation, a real convenient way of expressing all the significant digits and do it very efficiently. So for instance, 215, if I were to put that into scientific notation, assuming all 3 are significant, I would first of all get the front number, the first number, between between 1 and yet less than 1. So 215, if I were to divide that by powers of 10, divide by 10, divide by 10, 2.15 would be my multiplier right there. My power of 10, to get it there, would be 10 to the 2, because 100 is 10 to the 2. And this 215 can be written in scientific notation as 2.15 times 10 to the 2. Again, you can see it right here. Move the decimal point 2 places. That means that if you're going to the left, you're multiplying by a positive power, in this case power of 2. If you're going to the right, 1, 2, 3, okay, then the power of 10 becomes negative. Just some more examples of the same. Moving the decimal place 4, moving the decimal place 8, but here you're converting back. This 10 to the 4 represents shifting the decimal point to the right. This 10 to the negative 8, shifting it to the left. So scientific notation, it's helpful for indicating how many significant figures are present, but it's also very convenient for writing very large and very small numbers. We saw the distance between the Earth and the Sun is 150 million kilometers. Okay? You want to write that in a more compact form. Okay? Could have 2 significant figures, could have 9. But if we know it to 4 significant figures, we write it as, again, we want to get this 1.5, that's between 1 and less than 10. Did I say less than 1 before? What am I doing? So I'm going to move the decimal place 8 different times. That becomes 1.5 5 times 1.500 times 10 to the 8. When do we round off numbers? Okay. You use a calculator, you get more digits than you actually have precision. How do you decide which digits to keep? Well, the simplest rules are basically for multiplication and division, you keep the same number of significant figures as your worst figure. So, for instance, if you have one figure that's 3 significant figures and one figure that's 4, your answer is only going to have 3 significant figures. Okay, let's go through the different rules. Once you decide how many digits to retain, the rules of rounding off numbers are straightforward. If the first digit you remove is 4 or less, drop it and know the following digits. So let's say that you want to round 2.4271 to 2 significant figures. That means you're only keeping the ones column and the tenths column. You're going to get rid of these. This 2 decides whether you go up or you keep where you are. Decides the fate of 4. Okay? But since 2 is less than 5, okay, we're going to keep it where it is. It becomes 2.4. Here's another one. If the first digit removed is a 5, cutting it off at the 8 right here, then you round up. So 4.5832 gets bumped up, and our answer becomes 4.6. Again, rounding off's easy. We want 3 significant figures, so we only want 3 digits left. Okay? 1.5587, round up, 1.56. Here, these 2 are not significant, they're just placeholders, there's zeros in front, we knew that already. So we want 3 significant figures, we'll keep the 3, keep the 7, what do we do with the 4? Keep it where it is because 2 is less than 5, chop the 2 and 1 off, we get 0.00374. Here's where people get confused, they're like, oh, I'm getting rid of the 7, so I'm going to put a decimal place here. No! It's 1,367. I want to round it up to 3 significant figures. Leave a 0 here as a placeholder, but I'll round up to 6. So 1,367 becomes 1370. Okay? Don't cut off that thing and make it 137. That's wrong. 3 significant figures, so I'm going to cut off the 522, but 5 is greater than 5, it's 5 and up. 128 becomes 129, and 3 placeholders afterward. There we go. Finally, this one, we have 1.66. 6 is going to be my least reliable because I'm only going up to 3 significant figures. I round that up because of the 8, and there you get 1.67. Okay, so again, 4 significant figures, we do the same thing. Same thing. Notice I put in 0 placeholders where the non-significant figures were sitting. And again, kind of uncertain right here. The decimal point can tell you that all those zeros are significant. Let's do an operation right here. We're going to do simple division. My answer must have the same number of significant figures as my worst figure. 3 significant figures up here, 4 significant figures down there. Okay? So when I divide this by this 3 significant figure is a limiting factor. It doesn't matter if I have 100 significant figures. Okay? That 3 is the worst precision. So therefore, my answer will also have 3 significant figures. Now that's a rule for division and multiplication. What about for addition and subtraction? Multiplication, division, is the number of significant figures which is important. For subtraction and addition, it is the place, the power of 10, which is the worst. So for instance, I'm going to add these 2 numbers. Okay? 3.18 and 0.01315. Okay? The question marks there just mean we don't know what's in that column. We know to 3.18. Okay? Here we have 2 digits after the decimal point. It is good up to the hundredths point. Although the next figure is actually good to the 100,000s. It goes 3 more significant figures. Do those extra significant figures help you? No. They don't contribute. So my worst figure here, okay, is good up to the hundredths. So my answer, addition and subtraction, is also only going to be good up to the hundredths, or the second position after the decimal point. So let's do some of these. Okay? I multiply these two and my calculator reads out. What should my answer be? Well, my answer should only have 3 significant figures there. 49.7. What about this? 3 significant figures, 4 significant figures, so 3 significant figures. 46.4. 4 significant figures, wow, 6 significant figures. But again, my answer can only be good to 4, so that's what I get. 5 significant figures, 4 significant figures. Getting tired of saying that word. Answer is going to be 4 significant figures. 1.586 times 10 to the 7. Avogadro's number times this figure right here, 1.66. 1 times 10 to the 24. Good to 4, good to 4. No, my answer is going to be good to 4. There you go. Again, addition and subtraction. I try to line these up. You know, PowerPoint always shifts everything around, so I don't always get a great result here. But again, we add this to this, okay? And the answer becomes 59.77. Not quite sure what happened here. Ignore this right here. And this red line should be over right here. We're good to the tenths right here, so my answer is going to be good to the tenths. Subtracting this from this, again, my worst figure right here is good to the 100ths, so my answer has to be out to the 100ths. And notice, by subtracting by such a small number, it has no impact. This plus this, good to the units, so my answer is going to be good to the units. Oh, I know. This one right here, this little number right here, should have been over here. The formatting moved it over. Okay, and you can practice some of these. These are all in the PowerPoint. You can practice some of these. This plus this, we're good to the 100ths, so our answer is going to be good to the 100ths. This plus this, we're good to the ones, so our answer is good to the ones. This minus this, we're good to the tenths. Answer is good to the tenths. This and this, good to the ones, so our answer is good to the ones. It just happens to be 0. Mixed order of operation, you know, you always do the order of operation first, and then go on to the, follow the order of operation. Multiplication, division come first. Get your proper number of significant figures, then do addition and subtraction. So we do these two first, okay? These two, 4 significant figures, that becomes this. Then we do the addition. In that case, tenths is the best that we can do, so our answer will be good to the tenths. Same thing here. Now we're in parentheses, so we got to do this and this, this and this. Good to the hundredths, good to the tenths, good to the hundredths, good to the tenths. Okay? So the best we can do here, 4 significant figures, 4 significant figures, round this up to 4 significant figures. Okay? So, practice some of these, try to see that your answers match what we got here.